Let's consider the structure consisting of Zn excluding 0 together with multiplication modulo n. So here is our main question. Is that structure a group? Okay, so let's look for one case. Let's look at n equals 4. So when n equals 4, then we have our structure is Z4 excluding 0 together with multiplication modulo 4. Now, from the Cayley table for this structure, we see that when we multiply 1 times 1, we get 1, times 2, we get 2, times 3, we get 3, 2 times 1 is 2, 2 times 2 is 0, because remember our multiplication is modulo 4. So 2 times 2 is 4, but the remainder, when you divide 4 by 4, is 0. So the result is 0. 2 times 3 is 6. Reduce modulo 4 is 2. 3 multiplied by 1 is 3. 3 multiplied by 2 is 6. When you reduce it, modulo 4 gives you 2. And 3 times 3 is 9. Reduce modulo 4 is 1. So looking at this Cayley table for our structure, we realize that the operation is not a binary operation because closure fails. Furthermore, the element 2 in our set does not have a multiplicative inverse because 2 times 1 is 2, 2 times 2 is 0, 2 times 3 is 2. You never get 1 out of that. So when n equals 4, this structure is not a group. So going back to our original question, is the structure Zn excluding 0 together with multiplication modulo n a group? We have to say that that's not going to be the case all the time. So not always. Cannot be all the time because we have cases where it doesn't happen. Not always. Now, so we have to determine whether the answer is sometimes or never. Okay, so let's now generalize to see what failed in this particular example. What failed? Well, one instance is that the closure didn't happen. Observe that at the time we didn't get closure, the product gave a remainder of 0 when divided by 4. So this is giving us the condition that needs to be removed from here to possibly make it a group. So 2 times 2 is 4, which when you reduce it, modulo 4 gives you 0. So it is going to happen that if you have a product of two elements in general that gives you n and neither of the elements is 1, that you cannot have a group because the result will be 0. So let's examine that. So when n equals AB with A not equal to 1, B not equal to 1, you will never be able to have a group. Because it happens. What happened here will happen in general. So here's your KD table. So you have A somewhere around here. You have B somewhere around there. When you multiply them, you get N, but that's congruent to 0 modulo N. So in the KD table, what you will see is a 0. So the closure condition will not be satisfied. Okay, so if this is going to be a group, the only case is going to be, the only possibility that you have is the case when N is a prime. So let's answer that question then. Is Zn excluding 0 together with multiplication modulo n a group when n is prime? The answer, fortunately, is yes. As it turns out, if n is prime, then you will get a group. So that's our theorem for the day. So theorem, let p be a prime integer. The structure Zp excluding 0 together with multiplication modulo p is a group. Okay, so let's offer a proof sketch of this theorem. So first thing we need to question is confirm that the multiplication here is a binary operation. So well, we know. Okay, let's write first that this is our proof sketch. Okay, so first order of business, establish that this product is a binary operation on Zp excluding 0. So observe dot is well defined by definition of multiplication modulo p. So what is the well defined on the which set? The set is Zp. So we know that multiplication of elements in Zp is well defined, but the question is it well defined as well in Zp excluding 0? Well, it is still well defined because if you got a single answer, if you have two elements in Zp, and when you multiply them, you get a single answer here, that will happen in any of its subsets. And this set is a subset of that one. So also on Zp excluding 0. So the only thing we need to worry about is, could you, if you have two elements in the set, could you possibly get the 0 element? So if I have two elements in here, when I multiply them, is it possible I'm going to get 0? So let A, B be elements in Zp excluding 0. But suppose A dot B is 0. I contend this will lead to a contradiction. So if the product AB is 0, that means P is a multiple of AB. So this implies that P divides the product AB. But if P divides AB, but let's observe that P and A cannot have common factors, P and B cannot have common factors. So that's where the problem is going to arise. So observe, so since A is less than B greater than 0, the GCD between the greatest common divisor between A and P has to be 1. Consequently, since the GCD between A and P is 1, the only conclusion you can draw is that P then must divide B. But that's a contradiction because this is a contradiction because it is also the case that P is greater than B and that P is greater than 0. So P cannot divide a number that is less than itself. Okay, so we conclude that dot is a binary operation on ZP not 0. Okay, now let's check our group properties. G1, that the associative property is satisfied. Well, we're in luck. We already know that the associative property holds in ZP with a multiplication modulo P. So it is inherited. Let's say it this way. G1 associativity verifying associativity. So since the structure ZP under multiplication is associative, that's something that we already own. That's a known fact at this point. So is ZP minus 0. The ZP minus 0 is a subset of ZP, so the associative property is inherited from the structure ZP with multiplication. Next property. ZP minus 0 contains the identity element. So, existence of the identity element. And of course, that one holds because ZP minus 0 does in fact contain the identity element, which is 1. So 1 belongs to the set ZP excluding 0, and it satisfies the condition that 1 dot x is x and x dot 1 is x for all elements of the set. Okay, so far so good. One more property to confirm. That one, that for each element there is an inverse that's contained in the set. So G3, existence of inverses. Okay, so let's pick an element in our set. Let A be an element in ZP excluding 0. What we want to show is that there is some other element still in this set such that when you multiply these two together, you get the identity 1. Now, out of our 3 group properties, this one's the subtle one. How can you identify that there has to be another element in ZP excluding 0 such that when you multiply by this A, the result is 1. Now, we're going to have to think about complete residue sets. This is a number theory concept. So let's make it an observation that ZP minus 0 is a complete set of remainders, except it doesn't contain 0, right? So observe. Let me try that again. So, observe that ZP excluding 0 is a complete set of residues modulo P excluding 0. Because these are all remainders, but they exclude 0, so it is a complete set of residues. Excluding 0, because this does not contain 0. Okay, so here is a fact of number theory. If I take this set and multiply all of its elements by an integer, which is a relatively prime with each of its elements, then that will also be a complete set of residues excluding 0. So we have that if the greatest common divisor of P and some other integer, let's call it C, equals 1, then all elements of this set multiplied by C is a complete set of residues excluding 0. So let's say it this way. C ZP minus 0. So this means every element will be multiplied by C. So what's the result? This guy is a 1, 2, 3, all the way to P minus 1. So now I am multiplying each of these elements by C. So I'm going to get 1 times C is C, 2C, 3C, etc. P minus 1C is also a complete set of residues modulo P excluding 0. So we know that. That is a fact that we have to take for granted in this proof. It is a fact from number theory. So let's do the following. Let's make a choice. Let's make C be actually A. So let C be A. Why is that a good choice? Well, A belongs to that set, so it is relatively prime with B. So here's what we get. We're almost done with this proof. So we get that 1, 2, 3, etc. B minus 1 is congruent to, if we're letting C be A, then that becomes A, 2A, 3A, all the way to, so A, 2A, 3A, all the way to B minus 1A. So what happens here is that there is an element in this set that is congruent to 1. So there exists K in which of these elements is going to be 1, 2, all the way to P minus 1. So there exists an element in ZP minus 1, in ZP minus 0, excuse me, not 1, 0, such that KA is congruent to this particular entry of the left-hand side, modulo P. By definition of multiplication modulo P, that means that K times A equals 1. So by definition, K times A, where the multiplication here is multiplication modulo P, equals 1. And therefore, K is the sub inverse. So here, K is the inverse we were looking for. Okay, and that concludes our proof.